Let's face it, washing dishes can be such a hassle, but it is something that almost everyone in the world does every single day. Yet, how often do you think about the tool that you rely on the most, the dish sponge? What is it actually made of? Why do some of them fall apart quicker than others? And why do some of them last way longer than others do? My name is Valentina Duran, and this is my presentation on the material science behind dish sponges. I'll be taking a closer look specifically on polyurethane foams and how the chemistry, structure, and design affect their performance and sustainability. Let's start at the molecular level with chemical bonding. It's essentially what gives a sponge its strength. Your everyday run-of-the-mill sponge, such as Scrub Daddy, like the one I have here, which is a nicer sponge, and this one, a much more generic sponge, are made out of polyurethane foam. So what does this really mean? And how does this thing get made? Well, polyurethane is formed when two molecules react, an isocyanate and a polyol. A polyol contains hydroxyl groups. Essentially, it's these groups of OH hydrogen bonds, or van der Waals forces, that join together with the isocyanate and its benzene or aromatic rings. When this chemical reaction takes place, the result is a strong urethane bond, such as this picture right here. This is an example of some of the polymer chains that you can find in the polyurethane foams. The bonds in the polymer chain are covalent, meaning that the atoms equally share the electrons between them. The bonds make up the structure for the polymer, making it very stable and very flexible. While the hydrogen bonds do seem to be weaker forces within the chains are very, very long, sometimes spanning thousands if not millions of units, and the forces essentially strengthen with numbers. So why is it that we get this weird looking structure on the sponge? Unlike ceramics or metals that tend to have smoother surfaces, polyurethane does not form a regular repeating crystal lattice. Instead, it is made up of mostly amorphous structures. Amorphous structures look highly disorganized because of the cross-linking between the urethane bonds. The isocyanate's aromatic rings, or the benzene rings, make it really difficult for the long chains to line up nicely. It's kind of like introducing rocks to spaghetti. It's not going to break them, but if you just add them on top, they're going to be disorganized and all over the place, like this image right here. However, the polymer isn't always amorphous. There are regions that are very hard and stiff within the polymer, such as in this sponge right here, and they resemble semi-crystalline structures, like these ones in this image here. These images may look alike because they do have some of the same similar features, but semi-crystalline structures also have some really nicely organized, localized spots within the structure. And this allows for the sponge to be really reinforced throughout the material, such as Scrub Daddy, which is honestly a really good example of that. It lasts way longer. It's much easier to tell because of the rigid feel when it's dry, and when it gets wet, the sponge recovers and you can use it again and again and again. A key characteristic about this dish sponge and polyurethane foams is the intentional use of defects. We may not think of the porosity of sponges as a defect in polyurethane foam, but these are highly engineered during their manufacturing process to create an open cell structure, like the one that you see here. These cells are formed when a physical blowing agent, like this one, is introduced to the polymer mix. It creates bubbles throughout the liquid mixture, and it cures the thin wall cells, and essentially ruptures and leaves behind only the interconnected web of the pores that we can actually see within the sponge. These are called bulk defects, mainly because they are pretty big and visible to the human eye, but also because they're 3D and they surround the entire structure. It's what allows the sponge to absorb water and stay flexible. The size and density of these pores determine how the sponge feels and performs. Large pores create a softer, more flexible sponge that absorbs more water, like more generic store brand sponges. Small spores make the material feel stiffer, much more supportive, and more durable. But you essentially want a mix of these two, and you want to get to like a good spot to make a really nice sponge, like the one that you see here. Very different from this one over here. You get much more capability with these ones. The pore structure also impacts mechanical behavior. When the sponge is squeezed, these polymer walls, the little cell walls, they bend and they collapse and they store energy when that happens. When they are released, they do recover. Like if I compress this and then release it, almost happens instantly. However, if I continue to apply stress to it and compress it, it can cause permanent deformation or tearing, like some that you see here. A sponge's main use is in the water or in contact with other cleaning chemicals such as dish soap. In an open cell polyurethane foam, the interconnected pores really allow the water to move freely throughout the structure. And this is what these pores look like a little bit further up close. They are pretty big and allow a lot of air into them, which is because of that blowing agent. But this is what allows the water to go in through the material and get it and actually make it work well, so that when you clean your pans, you get soap actually coming out on the other side. The interconnected pores do allow the water to move around, which means that liquids can really diffuse quicker from the surface into the interior of the sponge, and it fills the sponge with soap and it helps it clean more effectively. But diffusion also affects the lifespan of your sponge as well. The water molecules don't only stay in the like around the polymer in the pores, but they can fuse into it as well. This especially happens over time and at higher temperatures. And diffusion can also help the sponge dry quickly, which is important for hygiene. You want fast moisture escaping because it gives the bacteria less opportunity to grow. However, the rate of diffusion really depends on the pore size and the manufacturing process in which the blowing agent is introduced to the polymer mixture. So it depends on the brand and how they like to make their sponges. Sponges with larger pores can absorb and release water quickly, but can also trap more food particles. Smaller pore sponges, like Scrub Daddy, although this one is pretty bad example since it's been used often, but they can restrict flow slightly and they keep the structure more supportive during their use. As I mentioned previously, the presence of water and other substances over time really start to break the polymer down, which is why you have to replace your dish sponge constantly. This is due to hydrolysis, the chemical breakdown of the polyurethane chains caused by water. The urethane bonds containing those NH and OH groups contain a polar carbonyl group where the oxygen strongly pulls electrons away from the carbon. This results in a positive dipole on the carbon, meaning that the carbon now really wants another electron, but it doesn't seem to have anywhere to get it from. However, when you introduce water to the polymer, the water molecules diffusing into the polymer can reach the urethane bond, and the oxygen in the water molecules can attack the electron poor carbon. This essentially breaks the bonds, the urethane bonds, and the polymer chain becomes shorter and shorter whenever this happens. This makes the sponge softer and less elastic and more kind of crumply. It's kind of when the smile starts to disappear. Hot water really increases the motion of both the polymer and the water molecules, and it helps them collide and react more often. And it also opens up the polymer structure so that the water can reach more of those urethane bonds. This is especially You can see this especially when you're working with hot water and cleaning like dishes. Like these are gonna deform more. They're gonna deform quicker and they're not gonna last you as long because of that. But heat doesn't only affect the long-term chemical breakdown. In sponges like Scrub Daddy, the polyurethane foam is very temperature dependent and it's intentionally made that way. It can almost instantly change the way the material behaves. Polymers undergo what's called a glass transition temperature. This glass transition temperature, because the polymer doesn't really degrade, it's meant to basically identify different ways that the material can act. Below the glass transition temperature, the chains have very limited mobility, so they're much more rigid and they behave like glacier. So when a sponge is placed in cold water, the polymer, the segments, the hard segments, they stiffen and tighten up and they can leave scratches like the ones here, which is really ideal for removing tough dried on food. And for Scrub Daddy, this is around 50 to 60 degrees Fahrenheit, and they intentionally make it that way so that it's easier for consumer use. They soften around higher temperatures at around 100 degrees Fahrenheit and above, and they start to deform more permanently. And once that sponge is exposed to the warm or hot water, the thermal energy increases the molecular motion. The polymer chains begin to rotate and vibrate and slide past each other, and it moves the foam structure into a rubbery state. It makes the sponge softer, more flexible, and gentler on delicate surfaces. This is more helpful when you need it to clean something that's hard to reach, or maybe something um, more delicate and fragile, something like glass. However, in Scrub Daddy in particular, they use a thermoplastic in their polyurethane foam, and this is very engineered and very patented material that I couldn't find too much information on, but it's essentially called a polycaprolactone. And it aids the polymer to help it have a lower melting point so that it's easier um, for the deformation to happen for consumers. This basically, um, the heat also interacts with the porous cellular architecture of the sponge, and there's so many air bubbles or the pores, and it traps heat very poorly. This is not a conductive material. It is much more like an insulator. It's why I can use this on a hot pan that I took right off the stove and not have it burn my hand immediately. It takes a little bit of time, and it takes more time, especially for foams like these and polymers like these. And one of the most important aspects of sponge performance is its mechanical behavior, how it responds to forces like squeezing, bending, scrubbing, and wringing. Polyurethane foam is what engineers call a cellular solid. So the mechanical properties are not only dependent on the type of polymer, but also the geometry of its pores, such as this picture right here. And you can see the geometry of these pores and how much they're enlarged to really show what they look like in the picture. When we compress a sponge, we're not compressing the entire block. We're bending thousands of little pieces of the cellular walls that deform and come back up, and it makes up the skeleton of the foam. At the strains, the struts elastically bend and they store more energy, which is why a really good quality sponge can avoid permanent deformation quicker. The good elastic recovery prevents a sponge from permanently flattening, like the one that we see here. This has pretty much been used forever and ever and has reached pretty much the end of its life. But as the strain increases, we get to more of a plateau region in the stress strain curve where it starts to level out. I have a picture of that right over here. Linear region, and then this is where we get more of that partial deformation happening. During this stage, the sponge absorbs a lot of energy without requiring extra force, which is really helpful, especially if you're scrubbing really hard. But tearing can occur, and that's when you get more into the permanent deformation, much more towards the end of the stress strain curve and into the hardening region, where permanent damage really takes place. You get much more tears, like you see here and here. Other foams like to use nylon fibers or some sort of resin or glue to strengthen its mechanical properties of the foam and of the sponge, but it's not going to last forever and you're still going to experience some deformation in the future. It may just slow that process down depending on the type of material that they add into it. The key factor here is really to controlling strength is really the density of the sponge. The sponges with smaller pores and thicker walls, thicker supports, tend to last longer because they are more capable of preventing deformation. It's not that it's going to prevent it always, but it's going to last longer and it springs up, unlike this one here. And premium brands have much higher compressive strength, so you can use them better to really get those areas that you really need to clean. And the lower density generic sponges really deform quicker, which is why you have to replace them after a couple of uses. And even though polyurethane sponges really perform well in cleaning, which is one of the main uses of them, at least in this way, they do pose serious environmental challenges. Polyurethane foam is made out of polyols and isocyanates, like I have mentioned earlier. Both of these are sourced from petroleum, the raw material that is used to make the polyurethane foam. Petroleum is a fossil fuel that requires intense drilling and refining, a process that contributes to pollution, to carbon emissions, and to really damaging ecosystems and to climate change, especially in these times. Once manufactured, the polyurethane foams are not biodegradable. They have very strong carbon-carbon backbones in the chemical structure, and the polymer resists the microbial attack, so that the sponges pretty much end up in landfills for hundreds of years due to the plastics, the microplastics within them. And because they are designed to be porous and flexible, they do wear down over time and they can release microplastic particles into the waterways, which is a much bigger issue that we're seeing nowadays with a lot of things that have microplastics in our lives, such as Tupperware and other much more common materials that we use in every day. This is one of them. The good news is that we do have alternatives. Cellulose, which is an alternative, which I wish I had with me, it's made out of wood pulp. We also have leaf sponges, which are also a natural alternative as well. And these are made from plant-based materials. They're renewable, they're biodegradable, and compostable. They do perform well for light to moderate dishwashing for the regular consumer, but they don't contribute persistent plastic waste like some companies that make these do. The cool thing about Scrub Daddy and the company that they run is that even though these sponges are not biodegradable, they do have a recycling program where you can give your used sponges back to them, and these sponges are collected and converted into industrial fuel for cement manufacturing. So they give them to the cement mixers and they use basically the petroleum, they melt these down and they use the fuel to operate those cement mixers, which does still pose environmental threats, such as this is still not going anywhere, it's just in a different form. And those gases are going to be going up into the atmosphere, which is going to cause environmental damage and more climate change. But it is still a good way of giving these sponges a second life before going straight into the landfill. This is a positive step, but recycling polyurethane foams is still very difficult and honestly not widely acceptable, especially when the sponge is contaminated with food and soap. Nobody really wants to use those anymore. So, from an environmental perspective, polyurethane sponges do provide great performance and durability, but they come at the cost of long-term plastic waste and fossil fuel reliance, which is something that at least we want to try to steer away from. Choosing biodegradable options when possible and disposing of synthetic sponges responsibly can really help reduce their environmental impact and their footprint. The performance of these sponges are driven by the polymer chemistry, the microstructure, and the environmental interactions of their materials. Polyurethane foams really provide versatility and strength because there's so many ways that we can engineer these with other materials, and you can have a lot of control in changing a lot of the properties of these. Polyurethane foams are great, but we do have alternatives like cellulose for a much more eco-conscious path forward. As engineers and scientists, it is our responsibility to analyze these trade-offs and innovate better materials for everyday life and for a more sustainable future. Thank you.